This is Vodcast 9B. In this unit we're going to talk about all the different gas laws. The first law we're going to study is called Boyle's law. He says there's a relationship between pressure and volume when you hold the temperature constant. So as you can see from this diagram, here's my pressure. This says 1 atm. And if I double my pressure to 2 atm atmospheres, if I increase my pressure, what happened to the volume of gas in this container? If you keep the temperature constant, the pressure exerted on the gas increases. 1 to 2, I increase pressure. What happens to my volume? My volume decreases. So if I could see the particles in here, what would be happening at a molecular level? I'm not decreasing the number of particles. It's still a closed container. I'm just pushing them closer together. So what am I eliminating? Some of that empty space. Here's a graph, if you like graphs, to show you that as pressure as pressure increases, the volume decreases. Or, if you remember from physics when we flip the graphs, if you normalize this graph, you can relate pressure and volume in a linear fashion if you graph 1 over the pressure. So the volume is equal to some kind of constant times 1 over the pressure. This is an inverse relationship. As pressure goes up, volume goes down. So if pressure goes up and volume goes down, and that's always equal to a constant, we can have an equation that looks like P times V equals a constant, which is P2 times V2. When you keep the temperature constant, as the pressure increases, the volume decreases. Inverse relationship. Now, how are we going to use this equation? Pressure, we said, was measured in atmospheres. Volume can be measured in liters. In this sample problem, it's measured in milliliters. So, if the pressure exerted on a 300 milliliter sample of hydrogen gas, 300 milliliters must be my first volume. I'm going to label that V1. If the pressure is increased from 0.5 atm, that would be my first pressure, and it's increased to 0.750 atm, that's my second volume, or my final, pressure. Pressure. My P2. What will be the final volume of the gas? So before you grab your calculator, let's think. What's happening to my pressure? It's going from 0.5 to 0.75. If my pressure is increasing, my volume should be less than 300. So let's plug this in. P1, 0.5 atm times V1, 300 milliliters, is equal to P2, 0.5, nope, that was my P1, 0.75. Here's my P2. Times V2 is what I'm solving for. So we do algebra. We multiply these two together. We have to divide both sides by 0.750 atm. So my V2 is equal to punch this in your calculator. Your final answer, V2, should be 200 milliliters. Just an equation. We don't need FLM for this one. That would be Boyle's law. Pressure and volume. Pressure and volume, Boyle's law. Charles' law. Charles' law says, I'm going to keep the pressure constant now. But I notice when I keep the pressure constant that there's another relationship between temperature and volume. 1 atm constant pressure, got that. If I increase the temperature, this says 200 Kelvin, this says 400 Kelvin. As I increase the temperature, what happened to my volume? As temperature goes up, volume goes up. It has to be a measurement of absolute temperature, which means I have to convert this to Kelvin. So, what's happening inside? What would the molecules look like? If you could see the molecules between container 1 and container 2, as you increase the temperature, we said the molecules do what? They speed up. As if they speed up, they either want to change pressure or change volume. If my pressure is constant, the only option I have is to increase my volume. So, as temperature goes up, volume goes up. This is a nice linear equation. We call that a direct relationship. As one goes up, the other one goes up. So V, you talk about rise over run, V over T now equals some kind of constant. So our equation, V1 over T1, is equal to V2 over T2. Again, has to be in Kelvin for the temperature. So here's our sample problem. A gas has a volume of 2.75 liters. Volume, V1, 2.75 liters at 350 Kelvin. We're already in Kelvin, so 350 K. That's equal to, what will the volume be? We're solving for V2, I don't know volume. If it is cooled to negative 50 degrees Celsius, here's the only curveball that can be thrown your way. Negative 50 degrees Celsius is not in Kelvin, so we're going to have to change that. K equals C plus 273. K equals negative 50 plus 273, or 273 minus 50, would be 223 Kelvin. Has to be in Kelvin. The units have to match, and it has to be an absolute temperature. Now, algebra, rearrange again. I can calculate my left side, but in order to solve for V2, I have to get it all by itself. How do I get rid of the 223 Kelvin? I have to multiply each side by 223. The kelvins will cancel, and I'll be left with liters. If you want to punch that in your calculator, you get a final volume of V2 equal to 1.75 liters. My temperature went down, so my volume should have also gone down. It's a good way to double check yourself. Our next law is Gay-Lussac's law. Lussac's law says when I have a constant volume, how am I going to do that? Well, if I just put it in a closed container, my volume can't change. Now there's a relationship between temperature and pressure. If this is an ice bath, I have a low temperature here, and I put it on a hot plate, and it starts boiling, I have a high temperature here. So if my temperature goes up, look what happens to the pressure. When temperature goes up, pressure goes up. What's happening to our molecules here? Same thing again. When I increase temperature, when I increase temperature, the particles want to move faster. If they can't expand, which was Charles' law, they're going to increase in pressure. As temperature goes up, pressure goes up. When they both go up, this looks very similar. I get a nice linear relationship again. They are proportional. They are more than proportional. It has a direct relationship. So we said, rise over run. P over T now is a constant, or P equals a constant times T. When P over T is a constant, our equation looks like this. P1 over T1 equals P2 over T2. Temperature, again, always has to be measured in Kelvin. So, our sample problem is a sample of nitrogen gas exerting a pressure of 0.25 atmospheres. That's pressure 1. At a temperature of 149 Celsius. What do I have to do with this temperature? 149 plus 273, 9 and 3 is 12, 5 and 7 is also 12, 2, 3, 422 Kelvin is my T1. The gas is then cooled. So my temperature goes down. When temperature goes down, remember Lusak's law is direct. When temperature goes down, the pressure should also go down. So we'll use that to check our final answer. The gas is cooled to 77 degrees Celsius. 77 and 273, 10, 15, 350 Kelvin. My temperature went down. To 350 Kelvin. What is the pressure? I'm solving for final pressure, or P2. Again, we're solving this the same way. In order to get P2 by itself, I have to multiply both sides by 350 Kelvin. When you punch this out on your calculator, you should get P2 is equal to 0.207 atmospheres. It was 0.250 to begin with. Now it's 0.207. My pressure went down because my temperature went down. Lusak's law is direct. If your temperature would go up, the pressure would be more than 0.25. Avogadro's law. Avogadro says I'm going to hold pressure and temperature constant. Why? Avogadro has to do with our conversion between moles and molecules. So now he says, get this, there's a relationship between the moles, the amount of your substance, and the volume that it takes up. Isn't that brilliant? So, for a gas at constant temperature and pressure, the volume is directly proportional. If I increase the amount, the number of moles, if I increase the amount, so if I blow more air in a balloon, it's going to take up more space. Here we have 4 different flasks: oxygen, helium, fluorine, and argon. If I have 1 mole of each substance, they have a different amount of grams, right? Because I can look on the periodic table and get the mass. My grams will be different, but it's all still 1 mole. Look at that. 1 mole, no matter what the substance is always equal to 22.4 liters. Okay? How are we going to use this? Nice linear relationship. Again, it's direct. As you add more moles, your volume is going to increase. Direct relationship, V equals a constant times N, or rise over run, volume over moles equals a constant. So we have 3 direct relationships and only 1 Boyle's law that was inverse. The equation looks like this. V1 over N1 equals V2 over N2. Sample problem. A balloon with a volume of 220 milliliters, that's my volume 1, is filled with 2 moles of helium. N has to be in moles. 2 moles of helium. Now, carefully watch the wording. What will be the volume, I'm solving for V2, if 3 moles of helium are added? Not the total volume is 3 moles, but 3 moles is added. So 3 moles plus 2 moles, my N2 has to equal 5 moles. Again, algebra, solving for V2. To get V2 by itself, I multiply both sides by 5 moles. When you multiply both sides by 5 moles, V2 should be 550 milliliters final. My volume got bigger because I added more moles to it. So, here's the key. The volume of 1 mole of gas at STP, standard temperature and pressure, this connects to Avogadro's law. Standard temperature, we said, was 0 degrees Celsius or 273 Kelvin, standard temperature, and standard pressure was 1 atm. Whenever you have 1 mole of gas, at these conditions, it's always going to equal 22.4 liters.